when we look at hydrogen bonding, okay, hydrogen bonding, we expect, okay, the hydrogen bonding to be bonded, the hydrogen, okay, being the more less electronegative element, okay, it's going to be bonded to either N, O, or F, okay, being the most nitrogen, oxygen, and fluorine, they are going to be the most electronegative in your periodic table. So if you have bonding between them, okay, that's actually going to be called hydrogen bonding. And of course, it's not bonding between. Okay, take note, maybe if you have, for example, water, if you have another molecule of water, so we are talking about the bonding between them. Okay, so again, if you have ammonia and then you have ammonia, so the bonding between them, HF, and you have HF, we are going to talk about the bonding between them. So the bonding between them, okay, is going to arise because, okay, if you actually make it larger a bit, okay, if you have oxygen, okay, oxygen, they have lone pair, okay, of electron, and then they have H. So I know that oxygen is going to be electronegative, okay, have ability to attract the electron to itself, and this is going to actually generally have a delta negative charge, and this is going to be delta positive and delta positive. Now, in order to understand this concept, okay, I will just put it this way so that we can see more clearly. Okay, so that is lone pair of electron. Okay, if you have, like, for example, ammonia, so the same thing, if I just follow like what I did just now, this is going to be lone pair of electron. It's not important, okay, but you will see much more clearly if you have like that. And HF, okay, take note, H is going to be bonded with F, but do remember F has 3 lone pair of electron. Now, if you want to actually identify, okay, the number of hydrogen bonds that they can actually form, okay, it is very important, okay, to identify that. Okay, in order to do that, okay, we can say that, okay, water molecules, they have in total, okay, one delta negative and another delta negative. So I'll put delta negative here and then delta positive here. If I put it over there, okay, I will notice that you have 2 delta negative and you have 2 delta positive. And the number of delta positive and delta negative is the same. It means that each of these delta negative can be bonded, okay, with other H plus over there, okay, with other molecule. Okay, let's say if I put H2O, okay, and then H2O, so they are bonded to H plus, okay. And then this one, okay, they are able to bond with H2O, okay, but I'll put it in this way, okay, with this O. And then same, if you have another H2O, they can actually be bonded. It means that all the parts, okay, of this water, they can take part in bonding. But let's actually look at how many hydrogen bonds that they can form per one molecule. So if you look at one molecule, okay, they have, okay, you have to actually divide by 2. Why? Because this one, okay, if you just focus on lone pair to hydrogen, so you have lone pair to hydrogen, lone pair to hydrogen, okay. And here is going to be hydrogen to another lone pair of oxygen. So we don't actually consider it's like either, if you are talking about hydrogen bonding, okay, so it's either lone pair to the hydrogen, okay, lone pair to the hydrogen, or it's hydrogen to lone pair. But once now I'm taking, let's say, from lone pair to hydrogen, I notice that, okay, in this particular molecule, okay, I have 2 hydrogen bonding. How about this then? Then they will be counted for this particular molecule. Can you understand this, Josh? Is it clear? Why is going to be 2?
Yeah, but
Okay.
sir, for
Yeah.
hydrogen fluoride.
Yes. Later
Why is
I'll
it
go
not like
to
more
hydrogen
than?
fluoride, Josh. Just hold on first. Yeah.
Okay.
So we go into that. Yeah. So this one is going to be 2 and 2. So this one we say maximum hydrogen bond can be formed. Maximum hydrogen bond can be formed. And this one we say that, okay, in one molecule, okay, in one molecule of water, the hydrogen bond that you can actually form is going to be 2. So there are total of 2 hydrogen bond per molecule for water. Okay, let's actually have a look at ammonia. Now for ammonia, okay, it's going to be slightly different. Okay, we have this being delta negative. This is going to be delta positive, delta positive, delta positive. If I put it over here, if I put delta negative and delta positive, how many delta positive and how many delta negative? I have 1, 2, 3. The ratio is not same. Okay, here you can see the ratio is the same. It means they can have a maximum number of hydrogen bond. It means all of them, they can actually take part in bonding. Okay, but here, if you have 1 and 3, okay, there will be 2 extra delta positive. Delta positive means hydrogen. So it means there will be 2 delta positives per 1 molecule that will not take part in the bonding. Okay, it means if you look at it overall, if you have a lot of ammonia, it means that, okay, you only have, okay, 1 delta negative, which is this one. And then of course, if you have more delta positive, it doesn't matter because there's only 1 delta negative. So only 1 hydrogen bond can be formed. Okay, it's like if you're going to a party. I think I went through some websites and I saw this, some very interesting way to compare. Let's say if you go to party and then there is 1 guy and then there's 3 girls over there. Okay, 1 guy with 3 girls. If you really want to couple up with 1 person or you want to actually hang out with 1 girl over there, you can actually only go and go and look for that 1 girl, and the remaining 2 girls will be just hanging out, okay, with themselves. So it means there will be in that party you have more girls compared to guys. So the bonding that is going to be formed is going to be quite less. So it means because of the ratio, okay, because there is only 1 guy, so they can only take part in 1 bonding. So it means if you have, okay, for example, ammonia, NH3, okay, if you have this, so it means they only can form with another molecule, H, something like this, okay. So it means that, okay, despite the fact that all of them can be formed, okay, despite all the hydrogen bonds can be formed, but do remember, when it comes to 1 particular molecule, when we count, it is going to be counted because of this 1 delta negative and 3 delta positive. There will be 2 hydrogens will go into waste. Okay, it will go into waste. So maximum you have 1 hydrogen bond. Okay, 1 hydrogen bond for 1 molecule of ammonia. I hope now it's much more clearer. Okay, it's one molecule of ammonia. So do you have any questions on this, Ashley?
No, sir.
Yeah. So are you okay?
Yeah.
Okay. Now let's actually go on. Okay, if you have HF, okay, if you have HF, how it will look now. Okay, this one, okay, the question that Josh was asking. Okay, this one, let's have a look at how many delta negative that you have. Delta negative, delta negative, delta negative. This is going to be delta positive. So if the same way, if I want to actually put it as delta positive and I have delta negative over there. So if I want to look at how many delta positive that I have only 1, okay, 1 molecule, and I have 3 delta negative, okay, 3 delta negative. This one, imagine you go to a party now, okay, instead of having a lot of girls, you have a lot of guys, and then let's say 3 guys, and then 1 girl. It's the same concept. Okay, 3 guys and 1 girl, that is going to be the ratio. So if let's say, of course, you don't go to a party of 4 people, okay. So let's say you go to a party which is going to be 12 people involved. It means let's say 4 molecules of each F. Okay. What will happen? Okay, what will happen? So you can actually see that out of this, okay, I know that okay, ratio 1 to 3. So it means that I know that 3 girls are there, and then I know that the remaining ones will be the guys. So I know that 9 guys will be there. Okay, 3 girls and 9 guys. So if let's say they want to pair up, okay, guys and girls, okay, ignore guys and girls, right? So guys and girls, okay, if they want to pair up, so what will happen? Okay, what will happen? It means we are going to have 3 couples over there. Okay, so it means if you look at one particular molecule, okay, one particular molecule, if you have one delta plus, they can only bond with one delta negative because okay, not enough hydrogen. So now what will happen? The two lone pair, okay, the two lone pair of electrons, they will go to waste. They will not take part in the bonding. Of course, they will take part in the bonding, but again, if you look at it overall, okay, for one particular molecule, okay, what will happen? Generally, there will be two lone pairs, okay, they will not actually take part in the bonding. Okay, so they do not actually form a maximum hydrogen bond that is capable. Okay, if you look at the capability, yes, you can actually have okay one bond here, you can have one bond here, you can have one bond here, one bond here, but okay, they do not perform up to their capability or capacity. Why? Because lack of hydrogen or lack of delta plus. So the delta negative will go to waste. Okay, similar to here. Okay, according to its capacity, you can have 4 bonds also, but okay, they don't utilize all because lack of lone pair. So only one will be formed, only one per one molecule. So here, so how many hydrogen bonds that they can form? Okay, so again, HF, for one molecule of HF, you only have one hydrogen bond. So in summary, okay, in summary, if I want to look at it, how do I look at it? In summary, when it comes to hydrogen bonding, okay, water will form maximum number of hydrogen bond to up to its capacity because okay, there are two delta plus and delta negative, so they will form one molecule. They will form two hydrogen bonding. HB is hydrogen bonding. And when it comes to ammonia and HF, they do not form up to their capacity. Is either because of lack of lone pair or lack of delta positive. So therefore, they only have one hydrogen bonding per molecule. Okay. So when we actually try to draw the boiling points, okay, if you want to compare the boiling points, so how do we compare the boiling points? Okay, let's say there's nothing over here in the x-axis. So if I want to compare the boiling point of generally, if you look at the reactivity, if you look at the electronegativity, okay, we do expect, okay, H bonded to NOF. So we do expect that H bonded to F should be higher. Okay, we expect like that. And then H bonded to O, we thought, okay, we will expect H2O to be here, the boiling point. And then being the a little bit lower, so maybe ammonia will be here. Okay, but sadly, okay, that do not happen, okay, in actual situation. Okay, it doesn't happen in the actual situation. What happens in the actual situation is, okay, the water, okay, they will overtake. Okay, they will overtake the HF. Okay, still HF will be higher than ammonia. So I will actually just put it over here. Ammonia, let's say this is ammonia, boiling point of ammonia. and then you have HF over here. And if you have, okay, water will be here. The reason why, okay, water, okay, the boiling point is higher than HF, okay, they do not follow the electronegativity, because water can actually form more hydrogen bond per one molecule, per one molecule. Or you want to actually mention that number also is fine. Okay, water can form two hydrogen bonding, where HF can form only one hydrogen bonding, ammonia can only form one hydrogen bonding. Therefore, okay, water has higher boiling point. Okay, water has higher boiling point. But the others, okay, like if you want to compare HF and ammonia, okay, why HF is actually much more having higher boiling point, okay, you can mention that the hydrogen bonding between HF with another HF, okay, the HF and another HF, this particular bond will be stronger. Okay, the hydrogen bond is stronger compared to the bonding between ammonia and ammonia. Okay, why? Okay, you can actually tell that, okay, fluorine, okay, fluorine, okay, they are much more electronegative than nitrogen. Okay, therefore, they will form much more, a greater delta negative that will result in higher boiling point or higher or stronger hydrogen bonding compared to ammonia. So that will explain about the graph that I showed you yesterday. So this one, okay, if you want to compare why the graph doesn't follow, why this one is contradicting with this graph, then you explain based on the number of hydrogen bonding. So the one that I want to correct from yesterday's lesson is this one. Yeah. So this one, on average, they will form one hydrogen bond. Yesterday I mentioned wrongly, which is two hydrogen bonds. So please take note. Okay. H2O per one molecule, they will have two hydrogen bonds. So I'll put it two hydrogen bond. Ammonia has one hydrogen bond. HF will have one hydrogen bond. The reason why these two are special, because there will be some sort of waste of the H plus, or there will be some sort of a waste when it comes to lone pair, okay, because of the imbalance of this delta negative and delta positive. So you just take note of that. Okay, so is there any question for this?